Hello everyone. In this video, we'll be covering CIE IGCSE physics, electromagnetic effects. Well, more like a small part of electromagnetic effects, which is uh, the force on a current carrying wire, uh, the right-hand grip rule or thumb rule, and how it's applied in cases of a current carrying wire, a solenoid, the Fleming's left-hand rule, and the working principles of a DC motor. So I'm assuming that you have a basic understanding of what electricity is, as in what a current or what voltage is, and also uh, the simple phenomena of magnetism, like what a north pole is, what a south pole is, what the direction of magnetic field lines indicate, and so on, right? So, if a wire carries a current, it induces a magnetic field around itself, a spiral magnetic field in this case, okay? And what the right-hand grip rule or thumb rule, both are correct, states that the thumb point towards the direction of the current. So in this case, the person's thumb is pointing towards like the top, so the direction of current is up. And the direction in which your fingers fold around the wire is the direction of the magnetic field. So in this case, the person's finger is curling around the wire like this. So the fingertip goes from here to here, and therefore this is the direction of the magnetic field that's induced, right? You have to imagine yourself holding the wire around your forefingers, okay, or curling your forefingers around the wire. And that's basically what the right hand grip rule states for a current carrying wire. To test yourself, put yourself in an opposite scenario in which this is the current carrying wire, okay? And in this current carrying wire, instead of the current going downwards, this time it goes upwards. What would be the direction of the current here? Well, if you've understood the right hand grip rule, imagine yourself holding this wire where your thumb points downwards. So your thumb points downwards. This is your thumb, imagine. So your thumb points downwards, and the fingers curl around the wire like this. Goes from here to here. And therefore, this is the direction of the magnetic field that's induced. I hope that makes sense. Right. Now, you must also know in IGCSE, like, what are the factors that affect the strength of the magnetic field that's induced. It's a very basic understanding, so you don't really have to go much in depth. There's only two factors that you need to keep in mind. This formula is not needed, the one which I'm going to write, but I'm going to write it down to help explain why the factors are what they are. So B is the magnetic field strength. Okay, so you see here that the magnetic field strength is directly proportional to the current. So the magnetic field strength is directly proportional to the current, and the magnetic field strength is inversely proportional to the radius from the center of the magnetic field. So assume that the center is like at the center of the current carrying wire. So because it's directly proportional to the current, the higher the current, the greater the strength of the magnetic field that's induced. And the further away from the center of the wire, the weaker the strength of the magnetic field that's induced. I hope that makes sense. Again, you do not need to remember this formula. I've just written it down to help explain, but you just need to know that the higher the current, the stronger the magnetic field induced. The further away from the center, the weaker the magnetic field induced. I'm pretty sure this is more easier to remember than this, so focus more on the first part. Now, this is it for wires. So what about for solenoids? For those of you who don't know, solenoids are basically wires that are coiled. So instead of like a wire going like this, you can coil the wire to make it go like this, right? So in case of a wire, the right-hand grip rule works a bit differently. So the way the right-hand grip rule works in case of a wire, a solenoid, is that your thumb points in the direction of the North Pole. So in this case, this is the North Pole, right? So your thumb would point in the direction of the North Pole, and your forefingers in this case indicate the direction of the current. So like, let's say the current is going like this, right? So it goes in, and so your fingers would curl around this wire. So when your finger curls around this wire, you see that your thumb points this way, and therefore this is the North Pole that's induced. So let's do a bit more complicated. All right. So let's say this is a wire, okay, and this is the solenoid that wounds around the wire, okay, and so the direction of the magnetic field. Okay, you know what? Let's make it less complicated. This is the wire, okay, and this is the solenoid that's around the wire, okay. So it goes like this, like this, like this, like this, okay. So what would be the North Pole here, right? So imagine yourself curling around the solenoid, okay. So when you curl around the solenoid, you see that the thumb points upwards. This is your thumb, it points upwards, and because your thumb points upwards, this is the direction of the North Pole, and this is the direction of the South Pole. Now let's move on to the next part, which is the Fleming's left-hand rule. Now what the Fleming's left-hand rule states is that, okay, before introducing you to the Fleming's left-hand rule, let's introduce you to a force that is exerted on a current carrying wire in a magnetic field. So let's say we have a North Pole here and we have a South Pole here, okay? So, and a wire is placed in the middle which carries the current, let's say downwards, okay? So from your idea of magnetism, you know that magnetic field lines go from the North Pole to the South Pole. I'll draw just one line to avoid complication. And in this case, the current is going downwards. So when a current carrying conductor is placed in a magnetic field, what happens is, because of the interaction between the magnetic field that's induced by the current carrying conductor and the magnetic field that already exists between the two poles, a force is exerted on this current carrying wire because of the interaction. And the direction of the force is given by the Fleming's left-hand rule. So this is the Fleming's left-hand rule, and you basically just hold your left hand in this orientation, each, like the thumb, the index, and the middle finger at 90 degrees from each other. So the direction of the thumb gives the force, the direction of your index finger gives the magnetic field, and the direction of your middle finger gives the direction of the current, okay? A way I remember this is basically an abbreviation where, because this starts with F and this starts with M and this starts with C, right? Because these are the initials, I remember this as father, mother, child. There's other ways to remember it as well, but this is the way I remember it and it sticks to me. Anyway, moving on to this question. So what would be the direction of the force that's induced on this wire, or exerted on this wire? So you see the middle finger is the direction of the current. So the middle finger would point downwards. This is your middle finger, okay? And the index finger would point in the direction of the magnetic field. So it's from this way to this way, from here to here. So it points in this direction. And you see, well, I can't draw this on a 2D plane, but basically, if you have done this right, your thumb should be pointing towards you. So in this case, the force would be exerted out of the plane. Basically, the force would be exerted towards you in this case, okay? And for a current carrying wire in a magnetic field, you can interchange the unknown variable. So let's say in this case, I found out the force, right? But in another case, if I was given, okay, and the current goes downwards, and I was given that the force is exerted towards me, and this is the direction of the current, how would I find out the direction of the magnetic field? Okay, imagine this isn't given, okay? How would I find out the direction of the magnetic field? Well, I know that the current is downwards, so my middle finger would point down, and I know that the force exerted is towards me, i.e. out of the plane. So my thumb would point towards me, and therefore, where would my index finger be pointing? So it would be pointing from left to right. So this pole would be north, this pole would be south, and the magnetic field direction would be this way. Okay, so let's try another example. So these are two poles, okay, unknown. No, wait, actually let's make this known, north and south. And this is a current carrying wire. And the current is being delivered upwards. So in this case, what would be the direction of the force? So you use the Fleming's left-hand rule here. So you draw a line from the north to south. So your index finger would be pointing from right to left. The current direction would be upwards. So because the current direction is upwards, the force, again would be out of the plane of the paper. The thumb pointing towards you. So the force would be out of the plane. In a similar situation, let's take, this is a current carrying wire, okay? And this is two poles, so south and north. And you're being told that the force is exerted into the plane of the paper. So your thumb should be pointing inwards. I shouldn't have said that, but take that as a hint. So what would be the direction of the current? Well, again, you use the Fleming's left-hand rule. So north to south, your index finger downwards, right? And did I say? Okay, so the force is out of the plane of the paper. No, sorry, into the plane of the paper. So it's towards you. Not towards you, sorry, away from you. So when your thumb should be pointing into the plane, and the magnetic field, i.e. your index finger, should be pointing downwards. And so the current direction is given by the direction of your middle finger. And in this case, if you're doing it right, it should be from left to right. So the current direction should be this direction, this way. Now the same principles of the Fleming's left-hand rule can be applied to a practical situation, which is the DC motor, and it's also something that's within your syllabus. So first of all, to explain the mechanisms, the working mechanisms of a DC motor, I'll just draw a diagram. Okay, I'll explain the diagram in a bit. So this is the wire, this is the slip ring commutator. There's actually a slip, there's actually like a space there in which it's not connected, and I'll get to that in a bit. This is the armature, and this is the poles. Okay. So from your knowledge of electricity and simple phenomenon of magnetism, you know that this is the positive and this is the negative terminals of the battery. And because it's the positive, the current flows from the positive to negative. So it flows like this, goes up this way, this way, this way, this way, and this way, right? And it comes back to the negative terminal. And the magnetic field direction is from the north to south, so this way. Okay. Now, instead of assuming, okay, let's assume that in this position it's into the plane. Okay, into the plane as in like the current is going inside the plane, and in this position it's out of the plane, so the current is coming outside, as in, so in this position your middle finger should be pointing towards the plane, i.e. the screen or the paper, and in this position your middle finger should be pointing outside the plane, i.e. towards you. Okay, so using the Fleming's left-hand rule, when you use it to find which direction the force is exerted, you will see that the force is exerted on these two armatures. Okay, before getting onto the mechanism, let's label everything. Okay, so this is, you have to know this diagram, or at least the apparatus used. So this is known as the split ring commutator. this is battery and this is the wire. I don't need to label that. This is the carbon brushes, and these are used because they are inert, so they don't react and conduct electricity or use up any of the electricity. And this is known as the armature, or you can also refer to it as a coil. No issues. So when you use the Fleming's left hand rule, you see that the direction of the forces exerted in this armature is opposite in each of the sides. So in this case, you would okay, here on the left, you would put the middle finger into the plane, and if you put the middle finger into the plane, the index finger should be pointing from left to right, right? So you'll see that the thumb points downwards if you're doing it correctly. So the force here is downwards, right? And in this case, it's coming out of the paper, so your middle finger should be pointing towards you. So in this case, the force is upwards, okay? And because these forces are opposite, what it does is it creates a torque. Torque as in like a rotation about this center. Like this is the center. This is not a very accurate center, but please bear with me. So it creates a rotation, okay? So when it creates a rotation, in this case, the rotation would be anti-clockwise, right? And this is basically the working principle of a DC motor. So when a current carrying wire that's arranged in the form of an armature is placed inside a magnetic field, it rotates. And this rotation, this kinetic energy, right, is used in many motors around the world. So that's its practical application. And that's basically the mechanism, the working mechanism of a DC motor. Now you may be wondering, like, what is the point of this? Like, why is there a split here? Because if there wasn't a split, and if the circuit was connected constantly, when the circuit, like, when the armature, it becomes like this, when it becomes like vertical, right? When it becomes vertical, it wouldn't rotate. Why? Because when the direction of the current is parallel to the direction of the magnetic field, no force is exerted. So let's say the magnetic field is like this, right? So is the magnetic field north to south, and this is the direction of the current. So unless the current is perpendicular, okay, not really perpendicular, but like in most cases it should be perpendicular, but basically it shouldn't be parallel to the direction of the magnetic field. If it is, then there is no force that's exerted. It can be at an angle as well, but that's beyond the scope of your syllabus, so we won't get into that. So that's basically the reason why there's a split. So the reason there's a split is because when it reaches this split, the circuit disconnects from the armature, and because the circuit disconnects from the armature, as soon as it disconnects, there's no current in the armature. So no magnetic field is induced into the armature, and because there's no magnetic field induced, there's no magnetic field of the coil itself. So there's no interaction of magnetic fields. So because of the previous motion, the previous torque that's already given to it, it continues rotating until the circuit is, the circuit is connected again. So it takes one complete round. So it's like this at first, okay? And then it becomes like this. And when it becomes like this, the split ring disconnects, and therefore it already has a motion this way, right? So it just continues that motion. So because it continues that motion, it rotates back down. And as soon as it rotates back down, the split rings connect again, allowing the continuous motion. I hope that makes sense. Anyway, to conclude the mechanism of a DC motor, this is basically the points that you must state. So you must state that you have used the Fleming's left-hand rule to find the force, right? After finding the force, you have to state the direction in which it's rotating. So using this diagram, in the diagram that I've drawn, you don't always get this diagram or the liberty to draw your diagram and then state the direction of rotation. But if you do, you have to know the direction. If you don't, you have to work out the direction. So with respect to this diagram, the rotation would be anti-clockwise, and the carbon brushes, as in these things, you have to mention that they connect the split ring with the battery. So carbon brushes connect split ring with battery. And then you have to mention that the split ring keeps the current moving. Like obviously the split ring is there for a reason, which I explained in detail, but you just have to outline that the split ring keeps the current moving in one direction. Okay, and if you don't really have to mention this every time, but if you want to, you can, and you have to say that at 90 degrees, that is when it's vertical, the split ring is not in contact with the brush, so no current passes through, allowing for free rotation. And yeah, it just keeps moving because of the inertia of motion. I hope you understood. If you have any doubts, please feel free to leave them in the comment section below.